Welcome to Unit 8, Lesson 2 on electric current. I'm first going to show you the worksheet you completed on 428 so you can check your answers. In Packet 3, you were given this worksheet titled Static Electricity. So if you want to get that and check your answers, I'm going to show them to you, or you could pause this or come back later. But I'm just going to give you a moment to check your answers just to make sure you had them correct. And again, this worksheet was in Packet 3. All right, from our textbook, I'm going to show you the digital lesson for Lesson 2 on electric current, so you can follow along with this digital lesson.
A city is beautiful at night as it is during the day. This nocturnal beauty can be seen because of the electric lights that shine upon its statues and buildings, and the Eiffel Tower illuminations that twinkle through the city's sky. Of course, none of this beauty would be possible without a ready supply of electric current continuously adapting to the needs of the city. Before we begin to look more closely at electric current, let's see some examples of it by clicking on the hotspots on the screen. It's hard to imagine how a city's electricity grid can operate so smoothly, especially when you consider how many people are turning off and on so many electrical devices. Sometimes there is a significant increase in the electric current that flows through a power line called a surge. A very short surge is referred to as a spike. Lightning like this often causes surges. Surges can also happen when electronic devices such as elevators, air conditioners, or computers share power lines. For example, several devices can be on at once and drawing electricity from the line. When an additional appliance is turned on, it causes a surge in the line to compensate for the extra demand for electrical power. When a surge of electric current goes to your computer, it can cause a lot of damage. The surge heats up the wires. Sometimes the extreme heat damages computer parts or stresses the wires, causing them to eventually break down. When a surge happens, it is not good news. Even if you don't have to replace your computer, you may have to have it repaired. What can you do to protect your computer or other electrical equipment? A surge protector helps protect electrical appliances from damaging electronic surges. Here's how a surge protector works. When there is a power surge, material inside the surge protector draws excess current away from the main line and away from the appliances plugged into that line. Using one of these handy devices protects the electrical appliances in your home and keeps your computer up and running. Welcome to the lesson, Electric Current. In this lesson, you'll learn about different types of electric current and how current, voltage, and resistance are related. The vocabulary terms for this lesson are electric current, voltage, and resistance. Click each term to find out more about it. Have you ever wondered what makes a light turn on and off? How can light appear as different colors? Why is one light dim and one bright? In this lesson, you'll learn how electric current works to light up the night.
And instead of clicking on each vocabulary word from that last slide, I'm just going to have each term introduced through this digital lesson.
Electric current is the rate at which electric charges pass a given point. Click each image to learn more about electric currents. This turnstile has a counter that measures the rate at which people pass through it. In a similar way, electric current is a measure of the rate at which electric charges pass a given point. Electric current is the rate at which electric charges move through a wire. The motion of electrons causes a current in the wire. The two different types of current are alternating current, or AC, and direct current, or DC. Batteries produce a direct current, or DC. In a direct current, the electric charge moves in one direction. The solar energy cell in this calculator produces direct current. So does the battery in a car. Some devices, such as hand-cranked radios or flashlights, generate direct current from mechanical energy. Another kind of electric current is alternating current, or AC. In this kind, the direction of the current changes. Click each image to learn more. This public utility company produces electricity. It sends the electricity out as alternating current, or AC. In an alternating current, the electric charges change direction, vibrating back and forth at a constant rate. The polarity of the current reverses about 60 times every second. These power lines come from a public utility company. The power lines carry electricity as AC to homes and businesses. Transmitting AC is often more efficient than transmitting DC because less energy is lost. Wall outlets provide alternating current. When this energy is used to power a fluorescent light bulb, the light is actually flickering off and on. The flickering is so fast, though, that you usually don't notice it. Alternating current is easier to transform into different voltages than direct current is. Many devices, such as a cell phone charger and the power cord for a portable computer, include adapters that change the voltage of AC current to a lower level that the device can use more easily. Direct current is one kind of electric current. Which of these devices works on direct current? Right. This flashlight runs on batteries and uses DC. Batteries supply direct current. Wall outlets provide alternating current that can be used directly by devices such as toasters, microwave ovens, and electric motors. Electric current is related to two other aspects of electricity: voltage and resistance. Click each image to learn more. Voltage describes the amount of work it takes to move a unit of electric charge between 2 points. The lower the voltage of an electric circuit, the less work is needed to move the electric charges. With higher voltage, the electric charges release more energy as they move. Voltage is also called potential difference because it's the difference in electrical potential energy between 2 points in a circuit. Alternating current provided in the United States uses 110 volts. In many other countries, it's 220 volts. Think of how you sip a drink through a straw. It takes less work to draw a given amount of liquid through a short, thick straw than through a long, narrow straw. You might say that the long, narrow straw resists the flow of liquid. In the same way, some materials resist or oppose the flow of electric charge. This opposition is called resistance. A material or device that opposes the flow of electric charge is called a resistor. The tiny coiled metal filament in this light bulb is a resistor. When electric charges move through the resistor, some energy is released in the form of heat. The heat energy causes the metal filament to glow brightly. The higher the resistance of a material, the lower the current in it will be at a particular voltage. Good electrical conductors, such as the copper wire seen here, have a low resistance, so electric charges move through copper very easily at a given voltage. Iron has greater resistance, so electric charges do not move through iron as easily as they move through copper at the same voltage. Several factors contribute to the electrical resistance of a device. Click each image to learn more. Different materials have different electrical resistance. Copper has low electrical resistance. It's used to transmit electricity. Nichrome, a material made up of nickel and chromium, has a higher electrical resistance. Because of its high resistance, electric charges moving through this metal produce energy in the form of heat. Nichrome is used in toasters to toast bread. A thick wire has lower resistance than a thin wire. Think of a water hose. A thick hose allows more water to pass through it and has less resistance than a thin hose. That's why high power lines and electrical cables are so thick compared to the wire filament in a light bulb. Short wires have less resistance than long wires. That's why power lines like the ones shown here are designed to be as short as they can be and still reach your home. Less resistance in shorter wires means that the energy gets to your home more efficiently. Resistance of metals also depends on temperature. Resistance decreases in the cold, but increases when metals get warmer. You've learned about resistance to an electrical current. Can you find which conditions lower resistance? Click your That's right. Resistance is lower at cooler temperatures. Way to go! Just as it's easier to drink through a thicker straw, there's less resistance in thicker wire. Great job! Lower temperatures and greater thickness make a wire have less resistance. Warmer temperatures and greater length increase resistance in a wire. Let's see what you remember about voltage. Which of the following best describes what voltage is? Click the correct answer. Not quite. The amount of charge. That's not quite right. Right! Voltage is an amount of work done by a unit charge that moves between 2 points. A good definition of voltage has 3 parts. It's an amount of work. It describes moving a unit of electric charge. And it refers to a distance between 2 points, like the 2 terminals of a battery.
All right, the next slide requires a typed answer, so I'm going to skip through that and go to the recap.
You've seen how You've learned a lot about electric current and how current, voltage, and resistance are related. Let's review the main ideas from the lesson. Electric current is a rate. A stronger current sends more electric charges past a given point in a certain amount of time. In direct current, or DC, electric charges flow in one direction. In alternating current, or AC, electric charges rapidly change direction back and forth. You use both AC and DC devices. Wall outlets provide AC current. DC devices use batteries. Voltage is the amount of work needed to move a unit of electric charge from one point to another. Resistance slows down the current. Some devices such as light bulbs and television sets are resistors. Many factors affect resistance. Type of material, thickness and length of a wire, and temperature all affect how much resistance there is in a circuit. Now that you've finished this lesson, if you wish, you can go back and review any part of the lesson again.
Our next lesson, lesson 3, will be about electric circuits. So I'm going to show you this clip right here on circuits, as there is some overlapping information, and then we'll look at the quick review.
When you put your thinking cap on and light it up, current flows through a circuit. Let's discuss 3 things that I made a short list for. They are current, voltage, resistor. Current is the flow of charge per second. It's measured in amperes. Got it good. Next is voltage. How bad a current wants to flow. And this one is easy. It's measured in volts. A lot of times voltage comes from a battery with 2 terminals. Here's what's happening. Know the tiny plus and minus on each end. They're positive and negative, and they send the current flowing because opposites attract with the closed circuit. it has its path. Resistors impede the flow of charge when they resist the current to use electricity. They're measured in ohms, they're all over your homes, in PCs, TVs, and cellular phones. More than one resistor can be on the same circuit, like these holiday lights with each bulb working.
Current wants to flow, but it needs a closed path. A series circuit has one path like a track. If it has more than one, that's a parallel circuit. I put my cap on and I work it. Current wants to flow, but it needs a closed path. A series circuit has one path like a track. If it has more than one, that's a parallel circuit. I put my cap on and I work it.
This string of lights is a series circuit with only one path for the electrical current. The voltage is shared and must pass through each bulb in the loop, diminishing the power, you see. The more bulbs connected, the dimmer they glow. And if the circuit's left open, the current won't flow. One burned out bulb leaves the circuit open. You gotta replace the bulb in order to close. How's your thinking cap doing? Is the bulb still bright? Well, let's discuss a circuit of a different type. In parallel circuits, each of the bulbs would be set up in paths, independent and complete. No shared paths, so each one gets full voltage from the energy source. And you'll notice turn one off, it won't affect the others at all. And the bulbs burn bright even if you add more.
Current wants to flow, but it needs a closed path. A series circuit has one path like a track. If it has more than one, that's a parallel circuit. I put my cap on and I work it. Current wants to flow, but it needs a closed path. A series circuit has one path like a track. If it has more than one, that's a parallel circuit. I put my cap on and I work it. And I work it. And I work it. Put my thinking cap on and I work it.
Resistors impede the flow of charge when they resist the current to use electricity. They measure electricity.
All right, let's take a look at the quick review. I'll read the questions and you can answer out loud or you can answer to yourself. Voltage is measured in volts. Name one place you might find a resistor in your home. PC, TV, cellular phone. How many closed paths are in a series circuit? 1. How many closed paths are in a parallel circuit? More than 1. What happens when more bulbs are connected in a series circuit? Each bulb glows dimmer. To end today's lesson, I'm going to ask you to go to Study Jams and type electricity, and you will then take the quiz. So if you type in studyjams.com, hopefully you will get to the site. If not, you can use the address right here and type that in to see if that helps. When you get to it, just type in electricity. Remember, again, this site is great for just math and science review. So click on current electricity and electric circuits, and you can watch the slideshow and then test yourself. Remember, the learning plan that I emailed to your parents at the beginning of each week does have the breakdown of what you need to do each day for physical science. And so for April 30th and May 1st, you're assigned to go to BrainPop. On one day, type in current electricity, on the next static electricity, and then take the graded quiz and then email me your results. Next week, we'll continue with electric circuits and more. I hope that you all have a great day. And again, if you need anything, just have your parent email me. I will see you later.